Hi, and welcome to Resonance in RLC Circuits. My name is Aoife Marsh, and this is an ECE 4823 project for Georgia Institute of Technology. First of all, a definition of resonance. Resonance is the tendency of a system to oscillate at a greater amplitude at some frequencies than others. To help illustrate resonance, I have two examples, a mechanical example and an electrical example, and in each case the damping is zero, because when the damping is zero, the resonant frequency is approximately equal to the natural frequency of the system. The mechanical example I decided to use is a simple pendulum, and as you can see here, how the amplitude is related to the swing of the pendulum. And as there is no damping, the phase doesn't change and the amplitude doesn't change. So the natural frequency is going to be the resonant frequency of the circuit. So the graph helps show this idea of resonance. The blue signal is the natural frequency of the pendulum, while the red signal is 0.75 times natural frequency of the pendulum. So this means that every fourth cycle, the forced frequency is in phase with the natural frequency, and this causes resonance. You can also see how the amplitude increases past what the natural frequency amplitude originally was, giving a max amplitude of the system. My next example is an electrical example, and electrical resonance means that the output voltage can actually be a greater voltage than the input voltage to the circuit. So for resonance to occur, the two impedances have to cancel each other out. So from the graph you can see that the input voltage is the signal in blue and it's at 1 volt, but the voltage across the capacitor is in red, and you can see that the output voltage across the capacitor is a lot larger than the original input voltage. This is because the forcing voltage is at the same frequency as the natural frequency of the circuit, which is causing resonance. So I'm going to look at three different types of circuits: a series RLC circuit, a parallel RLC circuit, and an extended circuit. So first of all, the series RLC circuit. You can see from the diagram, it has a resistor, an inductor, and a capacitor all in series with each other. And the voltage across the capacitor is the voltage that we're going to be examining and plotting against the input voltage. So the equation we need for the instantaneous voltage across the capacitor is shown, and the derivation for this is shown now. You originally get it by Kirchhoff's voltage law around the circuit, and you come up with the final equation as seen at the bottom. After this, you have to use Euler's method to approximate the solution. Inputs to the circuit have different effects on the resonance, and I'm going to look at three different inputs. First of all, the DC input can't create resonance in a circuit. This is because there's no changing frequency, which means that it can never be in phase with the natural frequency of the circuit. So the first example I have is a simple DC input with zero voltage, and as you can see, it has no effect on the circuit. Next example, I set the voltage to initially be 2 volts. So the capacitor starts off at 2 volts, and it starts to decrease due to the resistance. The example I looked at is an AC input, and there will be resonance at the natural frequency of the circuit. So in the first case, there is resonance, and you can see that the input voltage is 1 volt, but the output voltage across the capacitor is actually over 1 volt. It's about 1.3 volts, and this is because the forced input voltage is resonating at the same natural frequency of the circuit. So my next example shows slightly above the resonant frequency, and you can see from the diagram that the voltage across the capacitor in this case doesn't come close to the same amplitude as it did in the last case, and that its max amplitude is just below 1 volt. So I'd like to look at damping next, but I haven't gotten around to doing it because I was having some issues with the simulations. So after damping, I want to look at an RLC parallel circuit. So I haven't done any simulations for this yet, but I was going to look at the voltage across the capacitance again and show it against the input voltage. And the last one I wanted to look at was an extended circuit. And again, I'm going to look at the voltage across the very last capacitor. And I have a simulation of a ramp response input. As you can see, the input initially goes up very high and then saturates at 1 volt.